Hey there and welcome back. Today we're going to be covering pressure and wind part 2, right? We did part 1 earlier where we introduced these ideas of air pressure, pressure gradient force, Coriolis force, friction force, and how they all play together in order to determine the wind speed and the wind direction. So here we'll start out with a review, looking again at air pressure, pressure variations, and Coriolis force. Then we'll review the friction force. We'll put it all together, and then we're going to do wind prediction, which is basically exactly what the people do on the Weather Channel, what the TV people do when they forecast the wind. And then as a last section here, looking ahead a little bit, why all of this is important. Because ultimately, what we're getting then on Monday the 19th and then the 21st is atmospheric circulation, explaining global wind patterns. On the website you also have a worksheet that you can please fill out as you watch these videos or after you watch these videos. So let's get started here. And it all is about wind forecasting, especially at the surface, right? And the rules are pretty simple. Right? The direction is always from high pressure to low pressure. And at the surface, the wind always has to cross the isobars diagonally at an angle. The wind can never blow perpendicular to the isobars and can never blow parallel to the isobars near the surface. And the spacing of the isobars here, for example, right, they're very tightly spaced. That's a very steep pressure gradient, meaning you're going to have high wind speeds. And then here, for example, you have a wide spacing between the isobars. Pressure gradient is going to be pretty flat. Wind speed is going to be fairly slow. So really, the weather map tells you pretty much all you need to know to then figure out here, as shown on this map, wind speed and wind direction. Now, this is a computer-generated wind speed and direction map, but really, it's exactly the way done with the rules that you already know, right? So up here, see that high pressure area with the very wide spacing of the isobars. Well, there's hardly any wind there. That makes total sense. Highest wind speeds are here, sort of over northern Texas. And why is that? Why? Because we have a very tightly spaced isobar packages here. And then again, an area of very low wind speeds here, which is of course this area of very wide isobar spacing right here. So it is pretty straightforward to go from a weather map that shows you the locations of the highs and the lows to a wind speed map. Sorry, what? Where are we? Here we go. Sorry. Let's review this. Air pressure, pressure gradient force, and Coriolis force. So, differences in air pressure, that gives us wind. Wind brings us weather and climate. So that's kind of the fundamental connection, right? Air pressure isn't the same. Air pressure varies spatially. You know, there's always areas of high pressure. There are always areas of low pressure. And because we have differences in air pressure, we get wind. And wind effectively brings us weather and climate, right? And that's what a weather map does. The weather map shows you areas of high pressure, where are the lows, and how are the isobars packed. That's really what a weather map is. And then with a few simple rules, really, you can predict or forecast wind speed and wind direction. Right. So you can take any old weather map, here's an example, and sort of mentally try to draw in wind direction, now initially solely due to the pressure gradient force. So here we're assuming for fun that the Earth is not rotating, so there is no Coriolis force. There's only a pressure gradient force. And if that were the case, wind would blow from highs to lows directly down the pressure gradient, and the wind would blow across the isobars at a 90-degree angle. So you can think about the pressure gradient force as setting the air in motion, making the wind start to blow down the pressure hill from high to low. And then it's just a function of how tightly are the isobars packed, whether the wind speed is going to be fast or whether or not the wind speed is going to be slow. So pressure gradient force is what sets the air in motion. And you can draw in here the wind directions. Assuming again in this case that the Earth were not rotating, wind would blow straight down the hill here from high pressure towards the low pressure, going across the isobars at a 90-degree angle. Same case here. Same here. That's the theory if the Earth were not rotating. However, the Earth is rotating, and that gives us the so-called Coriolis force. And here we just have to memorize a few things. The Earth and the atmosphere are not glued to the Earth's surface. Therefore, if you will, the Earth can rotate underneath something that's flying in the atmosphere or something that's swimming in the ocean. And because of that, winds and airplanes and baseballs and whatever else floats around in the air are deflected to the right in the northern hemisphere. In the southern hemisphere, it's the other way. If you're a bird and you're flying in the southern hemisphere, if you're a rocket and you're flying in the southern hemisphere, you are deflected to the left in your sense of motions as you go from high pressure to low pressure. Same applies to ocean currents. So that's the Coriolis force, page 100 to 102. So now we combine the pressure gradient force with the Coriolis force, and in the upper atmosphere, if you're far enough away from the Earth's surface that friction becomes irrelevant, the pressure gradient force combines with the Coriolis force to make the wind blow parallel to the isobars. We call that a geostrophic wind. And that's what creates the jet stream, which we'll talk about in a few minutes. Upper atmosphere, two forces, winds blow parallel to the isobars. The laws of physics dictate that. Winds cannot blow across the isobars in the upper atmosphere. So there you go. All right. We got two forces. It's like your dad telling you one thing, your mom telling you the other thing, and you as the wind say, well, all right, I'll just have to do what both of you want me to do. And the only way I can do this is by blowing parallel to the isobars. That's the story. So here, for example, we have a high pressure, we have low pressure, and our winds here, that purple line, blowing parallel to the isobars geostrophically. Same situation here, blowing out from the pressure hill, getting deflected to the right, eventually blowing parallel to the isobars. Similar story here, blowing into the pressure low, getting deflected to the right, blowing parallel to the isobars. That's the upper atmosphere. At the lower atmosphere, you know, when you're close to the ground surface, when you're sort of below 5,000 feet, you have to add friction. All right, let's talk about friction. Let's talk about the friction force. All right. Friction simply means that wind speed is slowed. That's what friction does for you. That's how your brakes work. When you apply your brakes, you apply friction to your rotors, and that slows down your car. Well, that's the same thing that happens with respect to wind and friction from near a surface. Right? That friction diminishes the higher you go, and once you reach about 5,000 feet, there really is no friction anymore from the Earth's surface. So what that means is that near the Earth's surface, wind speeds are lower, wind is slowed down by friction, and that now reduces the Coriolis force. But it does not impact the pressure gradient force. I think that makes sense when you think about it. Friction has only an impact on the wind speed. Therefore, it only impacts the Coriolis force. The pressure gradients are not impacted by friction. So here's the upper atmosphere. No friction force. The Coriolis force is strong enough to match the pressure gradient force, and the wind is forced to blow parallel to the isobars. That's the purple line. In the lower atmosphere, again, there's friction that reduces the wind speed, that reduces the Coriolis force. And now the Coriolis force is weaker. And the Coriolis force is not strong enough to force the wind to change direction completely. You end up with a situation where the pressure gradient force is stronger than the Coriolis force, and the wind has to blow diagonally across the isobars. So in our little drawing here, we have a high pressure area, low pressure, and the resultant wind direction near the Earth's surface is the pink arrow. And compare that with the geostrophic wind if you were above 5,000 feet in the upper atmosphere. So that's the difference between wind direction near the Earth's surface and wind speed higher up. That's the story. Now, that's air pressure, that's pressure gradient force, that's Coriolis force, and that's friction force. Now we'll put all of that together, and then we have all the pieces we need to actually predict wind speed, to forecast wind speed and wind direction. And then we'll talk about why that's important. All right, so we'll see you in part 2.